Module 11, Personalized Diets. The history of the modern human diet is rife with misinformation, and many of the early recommendations about what we defined as healthy eating were driven more by commercial interests than by sound science. Dietary recommendations dating from the early 1940s have focused on food groups, with varying emphasis on particular groups over time. The various pyramid-shaped recommendations, beginning in the 1990s, were used to introduce a visual focus on which foods to emphasize and which to minimize. Most people agree that the weird pyramid from 2005, which meant to introduce physical activity but ended up looking like a pile of food, were not very intuitive to anyone. Today, My Plate depicts recommendations in terms of a dinner plate, which seems to resonate much more clearly as a public health message. But all of these recommendations are very generic messages of the way most people should eat. So how do we move from general to personal kinds of messages? Even at the most basic level, lots of nutritional personalization can take place. For example, across the lifespan, we know that different aspects of nutrition should be emphasized. For pregnant women, you might emphasize the increased need for folate, iron, and fluids. For babies, a big issue is whether or not they're breastfed or formula fed. For children, energy needs and appetites can vary widely from early childhood to late childhood. And for teens, we focus a lot on adequate vitamin intake and energy balance and avoiding the accumulation of excess body fat during this time of life. In adulthood, again, we keep our focus on balanced diets and limiting alcohol and possibly things like eating to reduce stress. And in later life, we might focus again on reducing intake to match energy expenditure, getting adequate hydration, and optimizing mental and bone health. These are just some very generic kinds of recommendations, and obviously for each of these life stages you could make much more detailed recommendations, but this is an example of personalizing diet based on stage of life. Disease status may also be used to create more personalized diets designed to address the special needs of certain diseases. For example, in obesity, of course, the diet is going to focus on weight loss and altering energy balance. In diabetes, the main focus might be on glucose control, for example. In heart disease, you may focus on a healthy vascular system, and that may be characterized by circulating lipids or other kinds of biomarkers that you would want to address and treat. In terms of cancer, you may focus on nutrition sufficiency given the stage of cancer or optimizing diet for optimal response to treatment. For immune response diseases, you may focus on diets that reduce inflammation. And for genetic disorders that we talked about early on, you may focus diet on improving quality of life and avoiding consequences like obesity that often occurs with early onset genetic disorders. And many elements of lifestyle are important to consider in order to maximize compliance with recommendations. For example, when you're recommending diets, you may want to assess socioeconomic status and cultural feelings and beliefs about food. You may want to ask about food preferences, food aversions, feelings of food security. You may ask about physical activity levels, and particularly for athletes, you may want to address the dietary needs of specific sports. You may want to ask about timing and shift work, and we heard in an earlier lecture that that's really, really important, and shift work especially puts individuals at increased risk for obesity. You may want to talk to the individuals about food preparation and their knowledge of nutrition and their skills in preparing foods. And of course, you'd want to assess the beliefs about diet. For example, Are you vegan? Are you strongly vegetarian? And your goals in terms of addressing diets. Do you want to lose weight? Do you want to improve your health? Do you have issues with food allergies? So all of those are ways in which diets can be personalized without ever looking at a gene or an omic measure. These will always be important things to consider when you're creating personalized diets. In addition to the impact of basic phenotypes and environments, we know that genotype at specific loci and across the genome can influence dietary outcomes. Genotypes serve to identify subgroups of individuals, which potentially can be oriented towards race ethnicity. But genes can also reveal new ways in which to target interventions based on the interactions between genotype and diet in determining outcomes, such as body composition. In these data from the Pounds Loss trial, you see in panel A the change in total fat, in panel B the change in fat-free mass, in panel C the change in fat mass percent, and in panel D the change in trunk fat percent. And in this trial, what these investigators showed was that genotype for a variant in the FTO gene was associated with change in body composition, but only in individuals who were eating a high-protein diet. So the panels to the right of each of these different sets of data indicate that for those individuals with an AA genotype, they see significant loss in total fat, in fat mass percent, and in trunk fat percent based on their genotype. And if you see to the graphs to the left of each panel, you see that there's no difference between genotype in individuals eating a low-protein diet. This might suggest that knowing genotype helps predict what kind of change will happen and what kind of diet you give to the person based on genotype. In this case, you'd want to give those AA individuals a high-protein diet if they're trying to see some change in their percent body fat. Another way to separate individuals is by potentially looking at functional differences by response to diet. Response phenotypes can be very revealing in terms of identifying the underlying factors that influence that response. An example of how personalized diets can be developed and prescribed using both phenotype and microbiome data is provided in this great paper by Zevi et al., in which the investigators recruited 1,000 subjects and characterized the microbiome, a dense array of blood markers, multiple questionnaires, including a food frequency questionnaire, and anthropometrics. Glucose control was their primary outcome, and subjects wore continuous glucose monitors for 7 days while documenting everything they ate with a mobile app. Although the experiment was designed to be free living, in order to compare within and across subjects for specific meals, the subjects were provided a simple breakfast for each of the 7 days. So you can see here in the center bottom figure, they were given 2 days of bread only, 2 days of bread with butter, 2 days of glucose pills, and 1 day of fructose, and then that allowed the investigators to compare both within subjects and across subjects for specific meals. The investigators took all of these data and then they used these complex and advanced machine learning techniques to predict optimal diets for maintaining blood glucose levels in their subjects. Then they took their predicted diets and applied them in an intervention study to test their predictive value. So here you can see some of the data from this study. This is just showing you the 7 days of continuous glucose monitor with one of the days blown up. And what they were doing is monitoring peaks and troughs of glucose over time and then putting markers on the data to show when the meals were being eaten. This area in blue represents the area under the curve, which is how they characterized the glucose response to meals. So here's some of the data to show that this is 4 individuals in 4 different colors, and they are all responding to exactly the same meal. So what they observed was that within individuals, there was highly reproducible responses to a given type of meal. But across the individuals, there was a great deal of variability. So here you can see that area under the curve ranged from 15 units for this individual at the bottom up to 139 units for the individual at the top. So widely ranging responses to exactly the same meal. This is a little bit more of the data that shows you that even though these individuals are eating this carbohydrate, the quality of the carbohydrate matters and the individual matters. So in panel 3, they're comparing the glucose meal to eating bread alone. And for the top individual, participant 468, you see glucose, a dramatic response to glucose in red, and a less dramatic response to the bread. And in the individual below, number 663, you see just the opposite. The stronger the response is in terms of bread, and the weaker response is in terms of glucose. So again, showing variability across subjects. And panel number 4 just shows some response to some free living food rather than the food that was given to them, comparing the glucose response to a banana versus a set of cookies. And again, you see the same sort of thing where the top individual is responding strongly to the banana and hardly at all to the cookies, and you see just the opposite pattern in the bottom. So what they did was they took all of these dense data. They had every 5 minutes they were monitoring glucose and all of the food intake data and all of the phenotype data that they collected. And collectively, they put it into machine learning algorithms to see if they could predict a diet that would maintain glucose control. So here you see in panels B and C, 2 measures that people generally expect to be highly predictive of glucose response. And that would be the carbohydrate percent in the meal or the calories in the meal. And what you see is that the correlations between either carbohydrate content or calories and postprandial glucose response is only around 0.38, only explaining about 15% of the variation. Conversely, the panels at the bottom, D and E, represent the prediction algorithm, which is correlated in panel D at 0.68, which explains about half of the variance in glucose response. And what they did was in panel D, they took 800 of the subjects and developed this prediction algorithm, and then they used it to predict response in the remaining 200. And you see this significant correlation. And so what was exciting is that they took this prediction algorithm and they created 2 sets of meals, one that would be predicted to be give the subjects very little glucose control, and the other that was predicted to give the subjects very tight glucose control. And here is a little bit of those data. You'll see this study described in more detail in a later video, but this is kind of astounding that this machine learning predicted diet had exactly the effect that they expected that it would. So the bad diet is the one that was expected to produce poor glucose control is in red, and the good diet in green. And what you can see is that there's a lot of fluctuation when the subjects are eating that red diet, and beautiful even glucose control when they're eating the green diet. So extremely strong data to suggest that these types of approaches for personalizing diet can be extremely powerful in determining the outcomes that are under study. So to summarize this short overview, phenotype data will always be useful as a foundation of personalized diets. I can't imagine that there'll ever be a time where age and BMI and gender don't add predictive value for the outcomes. But the exciting opportunity is that additional information can add additional value for determining a positive outcome. And that additional information should collectively add to the predictive value of the phenotype data. It's wonderful that we have the technologies to measure all these omic data, but the data should not be included unless it's adding to the prediction and improving the formulation of a personalized diet. Personalized diets can result in better outcomes than the standard of practice. And I think we have a lot of exciting potential in the future for using these data to create really effective dietary strategies. So the rest of this module will cover various ways that different types of omics and other measures have been incorporated to create these personalized diets. And you should be thinking about how you might use that kind of information to create a personalized diet yourself.